Hello, my name is Kevin Nguyen. This is Lab 3 for the black hole. Introduction. So our star is going to be orbiting a black hole. We're going to be given the star trajectory and the mass of the star. And we're going to figure out the mass of the black hole by using FNet. And to do this, I'm going to create a computer model of a star orbiting a black hole. So I use three equations: the gravitational force equation, momentum principle, F net equals delta P delta T over delta T, and the parallel, and then I split this into parallel and perpendicular components. So for our code, this is our initial condition. We're given G, gravitational constant, given mass of the star, and delta T is 1 day, which is equal to 86,400 seconds. T starts at 0. We're given X and Y velocity, and then we're going to find the change in X, so the change in delta X and delta Y by doing final minus initial, and then T is going to increase by delta T for each iteration. And this is the code for net force, and I'll talk more about that over here. So the net force is delta P over delta T. So delta dP over dt is equal to the parallel plus the perpendicular component. The parallel component is P hat times the change in magnitude of momentum over delta T. And then our perpendicular is the magnitude of momentum times dP hat over dt. So first I set up the V initial and V final. So the final and initial velocity. And then I did that to calculate the initial and final momentum, which is the mass of the star times V initial and V final. Then delta V and delta P, we do that by V final minus V initial, P final minus P initial. And dP dt is going to be delta P over delta T, which is also equal to F net. Now for our parallel component, we're going to find out P hat, which is going to be the P initial divided by the magnitude of P initial. Then we're going to find the d magnitude of the momentum over dt, so magnitude P final minus magnitude P initial over delta T. Then you multiply these two components together to find the parallel component. And then this is going to be equal to F net parallel. And then for our perpendicular dP dt, since we know it's Newton's second law, we can just subtract the parallel component over here to solve for the perpendicular, which is what I did. So dP dt minus dP dt parallel, which is equal to dP dt perpendicular, which is also equal to F net perpendicular. And what does the parallel and perpendicular component tell us? It tells us parallel tells us if it's speeding up or slowing down, and perpendicular determines how the curviness of the motion. And this is because of F net perpendicular, which is also equal to mv squared over r, where r is the radius towards the center of the kissing circle. So r is going to be a big factor in determining its curviness. So after calculations, this is what I got: F net parallel, and F net perpendicular. This is our star position and origin position, which is also known as the black hole position. And then this is the gravitational force equation. I just isolated for the mass of the black hole, and then I just plugged and chugged. And since we know the black hole position is at the origin 0, 0, 0, so I don't need it to add there since it won't affect the results. And this is going to be the mass of the black hole, which is 1.5 times 10 to the 34. And what does it mean? So what does it mean by the difference between the F net and dP dt and its parallel and perpendicular component? So F net is going to be the change in momentum over change in time, whereas dP dt is going to be our change in momentum over an instantaneous time. And that's also going to affect our parallel and perpendicular components. And what if? So what if the black hole was removed and a different black hole was placed in the same location? Motion of the star is unchanged and only affected by gravitational force. Can we tell the difference? And the answer is no, because F net would not change since the motion of the star is unchanged. And all the other variables are still the same. So G would be the same, mass of the star would be the same, distance between the two objects would also be the same. And this is my simulation. And as you can tell, as it gets closer towards the black hole, the magnitude of both parallel and perpendicular is larger, since it's stronger, closer, since the radius is smaller. And that's it. Thank you.